This video is an introduction to Gaussian beams so that you can complete the lab on Gaussian beams and Gaussian beam properties. The outcomes of this lab are to become familiar with Gaussian beams, which we will be using for our optics experiment. So it's a good idea for us to know what they are and how they behave. And then the content of the lab will help us illustrate how Gaussian beam propagation theory can be used to predict beam behavior. There are three lab objectives. The first is to try to do a series of measurements to find the beam waist of the beam coming from the laser and its Rayleigh range. Then we'll compare the measured Rayleigh range with the predicted Rayleigh range. Second, after focusing the beam, we will again find the beam waist and the Rayleigh range. Third, we will use short focal length lenses and attempt to pass the laser beam through a tiny pinhole. Introduction again to laser. Laser stands for light amplification by stimulated emission of radiation. And to get into more detail now, monochromatic we studied last week. We saw that the laser, the Heaney laser, is basically one color with a little bit of a line width. And the laser travels as a narrow beam. What I can tell you right now is that the laser does not stay the same size. It expands as it travels. The laser is polarized. We are just starting to learn about polarization. And today we're focusing on the mode. The mode means that the laser has a defined intensity profile. And in this case, the intensity profile is a Gaussian. So a Gaussian beam is a laser beam that propagates with a Gaussian intensity profile. The goal of this lab is to be able to calculate the following things: the beam spot, the location of the beam waist, which is the smallest point of the beam size, to find the radius of curvature, and then to also find the Rayleigh range. So we're going to go through all of these things in detail and come back to this slide. This will look familiar. Every traveling electromagnetic wave satisfies the differential wave equation. And in 3 dimensions, the wave equation becomes the following. The 3-dimensional wave equation is del squared psi. This will be familiar to us. Every traveling electromagnetic wave satisfies the differential wave equation. And in 3 dimensions, that wave equation becomes del squared psi equals 1 over v squared d squared psi dt squared. The partial derivative there is a Laplacian, which is the second derivative with respect to x, plus with respect to y, plus with respect to z. So we want to calculate Gaussian beam parameters, and the way we do this is we take a Gaussian beam function and we insert it into the 3-dimensional wave equation. We then solve for the propagation of a wave, choosing the z direction as the direction of propagation, and find important values. So our Gaussian beam is going to be written like this. This is a function psi of x, y, z, and t that's got an amplitude and a phase. When we substitute that expression and make the appropriate simplifications, we find that the amplitude, now this seems like a lot of steps, there are a lot of steps that happen in between here. The amplitude is some factor a naught times w naught over w of z, where w is the beam size, times e to the minus x squared plus y squared over w of z squared. That is a Gaussian. Our continuing to figure out what those different terms are, we find that the phase term becomes this. Becomes e to the ik, x squared plus y squared over 2r of z, times e to the I kz minus omega t. You notice here how, just to simplify what we're looking at, we pulled out the kz minus omega t, which tells us that it's a wave traveling in the z direction, and focused on the other parts of the phase just by separating the multiplication. All right, so now we have this expression for our Gaussian beam. Again, there are many steps that got us here, but I want you to have the feeling, the understanding, that The way we find our Gaussian beam parameters is by taking a function, putting it into the differential wave equation, and then solving for each of these parameters, the amplitude and phase. So we will focus on what we learn about these parameters. Again, the amplitude is this term and the phase is this term. The difference between the two is that the phase term is changing. It has this exponential. The amplitude is an exponential also, but it's not an oscillating exponential, while the phase oscillates with position and time. So what we want to do now is calculate the parameters W and Z. And that will tell us about these four factors. First, for a beam traveling in the z direction, the intensity of our beam is I naught e to the minus 2r squared over 2w squared, where w is the beam width. So this is a Gaussian. W, we will again see how to relate w to other parameters. The beam width w is inserted here into our Gaussian function, and r is simply the radius of the beam. Notice that for an aperture with a radius equal to half of the beam width, our intensity function becomes I naught e to the minus 2. And if we measured the total power transmitted through an aperture of the width with a radius equal to half of the beam diameter, then the total power transmitted through that aperture would be 0.86 times the maximum power existing in the beam, the total power in the beam. We will use this factor quite a bit in lab as we measure the power going through an aperture of a particular size. All right, let's return to our parameters. The Rayleigh range is the distance at which the beam size becomes W naught, the smallest beam size, times square root of 2. Okay, so let's look at this picture to explain what that says. The smallest possible beam for a focused beam or an expanded beam is called W naught, or W0, and that would be right here. The Rayleigh range is the distance over which the beam has not grown to be any more than W naught times square root of 2. So we would say that at this particular distance, the beam size is equal to square root of 2 times the minimum. And similarly in the other direction. So the Rayleigh range is this distance from one beam size to the other, one side of the focus to the other. What it tells us is how quickly a beam diverges. Imagine that the Rayleigh range is very long. That means that the beam size doesn't change much at all. The Rayleigh range is defined in terms of the spot size as pi times W naught squared over lambda. Well, the spot size is related to W naught. The spot size as the beam propagates is equal to W naught, the smallest spot, times 1 plus z over zr squared, square root. So what that says is, can we measure what should the spot size be at some distance away from the smallest spot? If we started here with our smallest spot W naught and want to know a distance z away, we could put in parameters, including the Rayleigh range, and determine the spot size. We will test that calculation with what we measure in lab. The radius of curvature is the curvature of the wave fronts as the beam travels. The radius of curvature is given by a function of z that depends on the Rayleigh range. But if we have a very large z much greater than zr, then this term becomes very, very small, and we find that the radius of curvature is approximately equal to z. So when it becomes important to use the radius of curvature, you can assume that it's approximately equal to z. This expression relates the radius of curvature before and after a lens, where the focal length of that lens is equal to f. Right, so now let's figure out where the location of our smallest spot is. Our beam waist at a distance z away from a lens is equal to the radius of curvature right after the lens, divided by 1 plus r over pi w squared over lambda. But if we're in a typical regime, then that reduces to the distance away from the distance to the smallest spot size equal to the radius of curvature. And the radius of curvature is approximately equal to the focus. So for a collimated beam going through a lens, the distance to the focus is approximately equal to the focal length of the lens. This is particularly important. I'm trying to box the important equations here that we're getting to. And our last equation is the beam waist, where we have this complicated expression for the beam waist, but given normal conditions, our beam waist is equal to lambda r over pi times w. We're going to ask a pre-lab question that relates to this equation, so take note of that expression. This part of the video will introduce you to the actual equipment we're going to use in the Gaussian beams lab, and mostly what you can do with it. The setup is the same as what we used in the first week, where we have our Heaney laser, and it is aligned. You want to check your alignment. You're going to use the same station you did last time. You're going to check your alignment, make sure that your beam is traveling in a straight line down the table using the aperture technique, and then reduce the light using a polarizer and potentially a filter as well to see your beam spot on a camera. So our most important piece of equipment today is going to be the camera and our aperture. So a couple of things about the camera. You'll be able to see this better, of course, on your own computer, but I'll show you quickly. When you go to camera settings, you can see that you can change the exposure, and you can either do auto, which will auto scale the exposure. That can be very helpful when you want to know an initial setting that'll be good to use. And you can also hold your exposure so that when the light changes, it won't auto scale. The next thing is this horizontal line profile. Select the horizontal line profile and use this to find the actual line profile of the largest, most intense part of the beam. When you go to the line profile, and that's this window up here, you can see the pixel number at each point along the profile. And that will be particularly important. We can find the width of our beam by looking at the line profile and the pixels on one side and the other. Okay, so the main thing you're going to use the camera to measure is the beam size. And how do we know how big it is? There are two ways of calibrating the camera, and I want you to use both of them. One way is to look up information about the camera itself and see if you can find pixel information, pixel size versus actual distance, so that you can see how big is this spot on the camera itself. Because that's what we're seeing. We're seeing light striking pixels on the camera. The second thing you can do is to measure the distance, is to correlate the pixel with distance. We have the cameras on a translation stage, and as you turn the knob, you'll see that the position of the beam changes. So what I want you to do is to mark the starting position and ending position for a particular translation and calculate the pixel size based on that. You can use other tools like drawing tools. There's a line drawing tool here where you could, for example, draw a line right through your mode or multiple lines. You can erase your lines. All right, so using the camera, that's two of the important things about the camera. You want to measure the mode size at different positions. Also, you're going to measure the mode size using a lens and how the mode changes as you move the camera to different positions or at different positions away from the focus of your lens. As long as your light is fairly dim after the camera, you can put your lens in anywhere. You can approximately center your lens by blocking the beam and then sliding your lens in till it looks approximately centered. Then look on your camera and see if you can find a little spot. on your camera. It's much easier when you get more familiar with this technique. So I see that that is where my lens is. Now I want to measure the intensity at this line profile. Well, that looks really too intense. See how it's maximized. The spot is too bright. So I'm going to decrease my exposure time until my spot is just the right intensity and I can measure an intensity profile. So there's another thing you can do is to change the intensity, the exposure time, which changes the intensity of the spot. That's lovely. It's a nice little spot. That's what you would like to see. You'll notice that as you move the lens to a position further away, your spot will be larger than it was before. And you can again measure the beam width, beam profile by moving your line that measures the intensity profile until you get a nice, what looks like an even profile of your intensity. All right, so you will use the camera in multiple ways to measure the spot size right at the focus of a beam, which means the smallest possible size, and then to measure the distance that you have to move the lens in order for the spot size to increase by a factor of square root of 2. That is going to tell you the Rayleigh range, and you will then compare that with a calculation based on your lens. The other thing that you may use to calculate your spot size is a power meter. So we have two power meters, this one and the Thorlabs power meter. And by measuring the power going through an aperture and closing down the aperture, you can see how whether the aperture is the same size as the beam. You can close down the aperture and then measure the power and see how that changes based on the aperture size. So that's another technique. It's a little bit less accurate than looking at the mode. I'll recommend looking at the mode and then checking it with the power measurement. Those are the only new components of the experiment today. So coming back to the lab objectives, your first objective is to do a series of measurements to find the beam waist, W0, and its Rayleigh range, Z sub r. Now, hint, the smallest spot as the beam exits the laser is right at the opening of the laser. So you could measure the spot size very close to the laser and then very far away. However, it may not be possible to find the Rayleigh range in the distance that we have set up on our table. It's a good idea to calculate what the Rayleigh range should be based on that minimum spot size, and then determine if you think you could reach it. 2, after focusing the beam to a smaller spot, we will measure the spot size at the smallest beam spot, and then find the Rayleigh range, and compare that with the predicted beam spot size and Rayleigh range. 3, use a short focal length lenses and try to get the laser beam the most power through a 50 micron diameter pinhole. And there, I want you to experiment with different ways of making the smallest possible beam spot, the smallest possible beam focus. So those are our 3 lab objectives, and you will understand these equations and principles as you go through the lab.